Welcome back. So today we've been talking in my classes about modeling sinusoidal functions or periodic functions. In other words, anything that repeats a certain behavior, we can probably model that with a sine or cosine function. So this is a problem just like we did in class today with a couple of different numbers. And if you see the link on your screen right now, the shortened Google link, I will also put a link to that in the description of this video. But if you click on that link, it'll take you directly to a PDF version of this paragraph and the whole questions that are kind of leading up to it. If you want to get that real quick, you can go there. That way you don't have to pause the video and write all this stuff down. It'll be right there for you. So basically what's happening is you walk by this spring, it's hanging there at equilibrium, not moving, and you decide to pull it down 7 centimeters and just let it go and kind of go back and forth. All I tell you is that you do pull it down 7 centimeters, it goes to a maximum height above equilibrium of 7 centimeters, and it takes 1.9 seconds to get from the minimum to the maximum value. Just from that information alone, we should be able to model a sinusoidal function. That's your big word of the day. We should be able to model a sinusoidal function to explain this behavior and explain the height of this weight at any time after you let it go. So what are some questions we need to ask ourselves? First thing, what is this going to look like? If we graph the x-axis as time and the y-axis as the height, what will this graph end up looking like? You can probably know already, since we've already kind of mentioned the word sinusoidal. And by the next questions, what's the amplitude and period? Probably going to be one of our trig functions. And then some other questions there for us to kind of discuss and look through that. So let's look at the graph first. What is this thing going to look like? I've got a little animation here that'll show you kind of what's going on, right? So you come down and you get that minimum value, and the line for the minimum value is there. It goes up to the maximum value here, and your equilibrium point would be right here on that dotted line. So what are my values going to be? Well, I know I'm pulling this down by 7 centimeters, so that'd be a -7. And then it's going to a maximum value of +7 centimeters. And if you're watching this video, you should know what amplitude means with relation to the middle of that wave. So that means our amplitude is going to be 7. How about our period? Well, again, if you have a good understanding of the sine and cosine functions, we know that period is the time it takes for one complete cycle. Or if you're more in physics line, a wavelength. But if we talk about the time it takes to go from, for example, one minimum to the next minimum, how long would that be? Well, we know that it takes 1.9 seconds to get to the maximum value from the minimum. So if it's 1.9 from the bottom to the top, how long will it take to get back down to the bottom? That would be another 1.9 seconds. So our period, 1.9 times 2, would be 3.8 seconds. And then, of course, we also know from trig functions that when we want to write a function, we have to get the b value for our function. And we should know that by now is 2 pi over the b value, so 2 pi over 3.8. Will be my b value. I could simplify that. I'm not going to worry about it because this is going to end up being graphed on a calculator anyway, so we can answer the final questions. So I'm not even going to worry about simplifying that. Where's my equilibrium point? Well, that's this dotted line here, and we're going to call that 0, since I'm kind of moving down 7, negative direction, and then back up 7 in a positive direction. So I can call that my equator, or my x-axis, really what it's going to be when you end up graphing this. How about the next question? What is the position at time equals 0? So again, you're walking by this thing, it's just hanging there, steady, not moving. You pull it down, you're 7 centimeters, and you let it go. The time you let it go is when it's at that low point. So the position at time equals 0 is at -7 centimeters. So that's my initial value. So that's going to help us out when we go to write the actual equation. And then the last question I have for you here, when does the weight first pass through equilibrium? I'll let you think about that for just a second. Well, if we know that it takes 1.9 seconds to go from the minimum value to the maximum value, what part of that would be just passing through equilibrium? We know from graphing that the sine function or cosine function is divided up into 4 equal parts. So from low to high is half of the total period. So we can cut that in half again and get when it passes through that equator or the equilibrium point. So it'd be 1.9 divided by 2, which would be 0.95, is going to be your when the time passes through there. There is going to be one thing on here that I'm not going to do on the video here, and that's writing a second equivalent model for this. But if you look on the PDF, there's one where it says use the other trig function, and that's where that value would come into. Okay? So there's all our information. We have our A value, our amplitude. We have our B value. There's really no K because my K is 0 since I'm using that equilibrium point as 0. And so I think I'm ready to go. Okay? So what would our model be? What's our model going to look like here? We know A is 7. We know B was the 2 pi over 3.8. The K was definitely 0. But look, since I'm starting at that minimum value, since my graph is really going to end up looking at my y equals 0, it's going to look something like this, right? Where that's -7. I know if I start at a minimum value, it's going to be easier to write this with a cosine function. Okay? So since I'm starting at a minimum value, my equation is going to look like -7, since I'm starting at a minimum, not a maximum, cosine of 2 pi over 3.8 x. And that's it, because I'm starting at t equals 0, so I'm starting on the y-axis, so I don't need any kind of phase shift, and I certainly don't need any kind of k value, because my equator was at that 0 value, at that 0 height. Okay? And if you have a graphing calculator handy, we can put that function into our calculator just the way it looks, and then we can adjust the window. On the PDF that I linked to, we want the first 20 seconds of the function. So my x-min, x is time, so we can go from 0 to 20. And then the dimensions of the height, where can we go to? I know it's 7 to 7. I like having a little bit of extra room. So my dimensions on the calculator can be from -9 to 9, just to give me some space on the top and bottom. So what would that look like? That's going to look like this. Okay, and you see, I went a little bit beyond 0 just to kind of give me some more space. So this is my initial value of -7, and you see all the different patterns all the way, and actually ended up going out to 30 seconds. And you see kind of what kind of the spring's behavior over time. So from there, we can look at different questions once we have that thing graphed. I'm not going to take the time to answer these on the video, but if you have a graphing calculator, we should be able to get these questions out and answered fairly directly once we have it graphed correctly in the correct function. Okay? So that's your spring motion problem, pretty straightforward, no K value or anything like that. What we're going to do tomorrow in class, and the next kind of step along these lines, is a question like this. And I don't have a PDF uploaded for this, so if you want to pause the video real quick and just kind of take a look at these values, this is kind of a different animal. So I'm using the big Ferris wheel they have in Las Vegas called the High Roller. You see the maximum height. is 550 feet. The platform when you get on is 30 feet above the street. And the wheel is rotating at a speed of 12 inches per second. Holy cow. And some constant motion, so we want to be able to model a function that is going to tell us the height of one of these capsules at any time after they get on. Okay? This is a little bit trickier. I'm not going to do this whole question because I don't want to steal my thunder from the next day, but let's kind of label some of these sides right here and kind of label this thing. So I know my total height from the very top down to the ground. And I'm going to go back and forth a couple times. The maximum height was 550. And I also know that the platform where they get on is 30 feet. So from we'll call it right here, that's 30 feet. So what do we have to find out in order to do this? Well, the only thing that's rotating is the wheel itself, right? So we have to find the diameter, which will go from here through the center down to here. We should be able to do that. From there, we can find the amplitude, because notice, if I call this my center point, we can also, and by the way, we can also find this distance right here, because that will be my K. So that's going to help me with my amplitude and my K value. And then the trickiest part of this is we need to find how long it takes for one of these capsules to go all the way around. And the only thing we are given in this problem, we're given that it's traveling at 12 inches per second. So we need to, the easiest thing to do probably would be to convert the diameter to inches, find the circumference of that Ferris wheel. Once you have the circumference in inches, we can divide that by the rate, and that will tell you how many seconds it will take to go around. And then we can take that number and figure out how many minutes it will take to make one full period. I'll let you stew on that. So what would that end up looking like? We would take the 12, so we would take 550. Check that, we'd take 520 because the diameter is 520. So we would take the circumference is 520 times pi, but we have to multiply that by 12 to get it in inches. And then we take the circumference divided by how fast it's traveling, and then multiply that by 60. Oh, I'm sorry, divide that by 60 to get how long it would take in minutes to go one full revolution. Okay? So that's kind of a preview of tomorrow. You have to be able to find the diameter, the amplitude, the rates, all that good stuff like that. And again, would you use a sine or a cosine? Notice they enter onto the Ferris wheel at the bottom of it, so that should give you a hint of what you're going to use, sine or cosine. And then there's going to be a second problem tomorrow, which I'm not going to get into in the video, about tides down at the coast. You've got a boat tied up at the dock. But we'll work on that tomorrow. I hope this did some better explanation of spring motion and at least kind of give you a preview of things to think about as you come into class tomorrow. Again, there's a link in the description, and there'll be some links at the end of this video about graphing some sines and cosines and writing equations once you have all the information. Okay? Hope this helped you out. Have a great evening. We will see you next time.